Hello, scholars. So today we're going to be looking at big idea number 2B, complex numbers. So our learning targets for today, I'm learning to perform operations with pure imaginary numbers, and I'm learning to perform operations with complex numbers. So the first thing we really need to define is what is an imaginary unit. And that are those numbers that are like the square root of a negative. And in this case, specifically a -1. Up until this point, we were telling you are not ever allowed to have the square root of a negative number. However, now I've come to the point where we can. They are called imaginary numbers, and they are defined as such. The square root of -1 equals I. So, therefore, what happens if I were to square -1, the square root of -1? Well, I end up getting the square root of -1 times the square root of -1, which we know a square root, when squared, cancels out. And I'm just left with the answer of -1. So that's what an imaginary number is. Pure imaginary numbers actually are the form of BI, where B is the real number attached to my imaginary. So let's go ahead and take a look at what that gets us from here. We have some examples. The first one says to simplify. I have the square root of -27. The way I like to approach problems like this is I'm going to take my 27 and I'm going to find all my factors. I'm going to start at the beginning and go to the end. So 1, 27, 3, 9. Well, that was a very short list. All right, so now I'm looking at the square root of 27, or -27, and I'm looking at the factors of 27. I'm going to look for the largest perfect square. And remember, perfect squares are 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, so on and so forth. So in this case, we just said it. 9. 9 is a perfect square, so I'm going to choose the number 3 times 9. And now I'm going to take this -27 and I'm going to split it into 3 parts. Well, we know that 27 itself splits into square root of 3 times the square root of 9. But how did we make that a negative? Well, that is where this -1 comes into play, because 3 times 9 times -1 equals that -27. So can we simplify the square root of 3? No, it stays the same. Can we simplify the square root of 9? Absolutely. The square root of 9 is 3. And then can we simplify the square root of -1? If you said yes, you are absolutely correct. We know that the square root of -1 is that I value. So now I'm just going to put I. All right, so when I write down this final answer, the square root, whatever it is always going to come at the tail end. So now my final answer is 3I square root of 3. And that, my friends, is the final answer for the square root of -27 simplified. So let's take another look. Let's take a look at the -216. So I'm going to make the factors of 216 itself. So here's my 216. I have 1, 216. No perfect squares yet. 2, 108. No perfect squares yet. 3, 72. No perfect squares yet. 4, 59. No perfect squares yet. 5 doesn't go into 216, but 6 does. We have 6 and 36, and there we have it. 36 is going to be our largest perfect square in this case. So I'm going to go ahead and mark that I'm choosing 6 and 36. And now I'm going to break this down. -216 is the same as square root of 6 times the square root of 36 times the square root of -1. All right, let's simplify this down. Can the square root of 6 be simplified? No. So we just bring it down to the square root of 6. What about the square root of 36? In fact, it can. 6. And we know that the square root of -1 actually goes down to simplify to that imaginary number I. So when we write our final answer, we have 6I square root of 6. And that is that answer. Now this is a concept that you'll see very frequently on the ACT, and it's one of those that can be quickly done. So we're going to do 2 more examples of just pure simplification. All right, so we have 18, my factors of 18, 1, 18, no perfect squares yet, 2, 9, there we have it, we have our perfect square, 2 and 9, 9 being that perfect square. So now we're going to break this down, square root of 2 times the square root of 9 times the square root of negative 1, because 2 times 9 times negative 1 gives us that negative 18 value. The square root of 2 does not simplify, but the square root of 9 does, and we get an answer of 3. And then once again, we have the square root of negative 1, which gives us that I value. So I have 3I square root of 2, because that square root is going to come at the end. And that is only actually occurring when we have these monomial terms. Monomial meaning one term. When we have more than one term, it'll look a little different. And we're actually going to talk about that a little bit further into this video. So let's take a look at this example. Negative 125. Let's find our factors. 1 and 125. 2 does not go into 125. 3 does not go into 125. 4 does not go into 125, but 5 does. 5 goes into 125 25 times. That means I have 5 quarters for $1.25. So we now know that 25 is a perfect square. That's one of the ones you guys always remember for some reason. And now we're going to split this up. Square root of 5 times the square root of 25 times the square root of negative 1. All right, the square root of 5 does not simplify. So we bring it down. The square root of 25 does. Nice 5. And then the square root of negative 1 is that I value. So we have I. So our final answer becomes 5I square root of 5. All right, so up until this point, we've only been working with a singular I, the square root of negative 1. However, we can look further into it. So 1I is just I, because it's the square root of negative 1. But I squared itself is square root of negative 1 times the square root of negative 1, which is negative I. I cubed is the same as negative I, and I to the 4th is just that positive 1. This is the one we really want to take a look at, I to the 4th. Because if we can get anything into the terms of I to the 4th, it'll really help us simplify later down the line. All right, so now we're going to simplify a little further. So it says negative 5I times 3I. Well, this is just commutative. We're going to multiply our b values and multiply our I values. So negative 5 times 3 is negative 15. I times I is I squared. Well, do we know what I squared is? In fact, we do. We know that it is negative 1. So I'm going to replace I squared with negative 1. Well, at this point, now I only have 2 real numbers. Negative 15 times negative 1. 2 negatives make a positive, so my answer here is 15. Nice and easy, right? All right, this next example, we have our numbers already in square roots. We have the square root of negative 6 times the square root of negative 15. There's actually several ways we can go about doing this. I'm going to multiply negative 6 and negative 15. All right, when I multiply a negative 6 times a negative 15, I get a square root of 90. Notice my negatives are gone, so I know this is going to simplify. The factors of 90, 1, 90. 2, 45, 3, 30, 4 does not go into it, 5, 18, 6 goes into it, 15 times, 7 does not, 8 does not, but 9 goes in 10 times. So which one is our largest perfect square? In this case, it is that 9 value. So I break this down, the square root of 9 times the square root of 10. Well, we know the square root of 9 is 3, and the square root of 10 is just the square root of 10. And there's that answer. All right, now we're going to solve. And Miss Younger forgot to put equals 0, so she's going to put it right there now. So it says solve x squared plus 64 equals 0. Well, you guys should know at this point that when solving for an equation, we always have to isolate that variable x. So first things first, let's subtract the 64 from both sides. Awesome. So now those 64s cancel, and I have x squared equals a negative 64. All right, up until this point, this is where you guys would have stopped, because we would have said, hey, you can't take the square root of a negative number, but now you can. So now we're going to take the square root of both sides. Well, we know on the left-hand side we get x. But this is the same as the square root of negative 1 times the square root of 64. Well, we know that negative 1, the square root of negative 1 is I. We know that the square root of 64 is plus or minus 8. So x equals plus or minus 8i, because remember that real number, that b value, is always going to come to that front. All right, let's talk about complex numbers in general. We've been talking about those monomial terms, but now what if we have that binomial term, meaning two terms? A binomial actually takes the form of a plus bi, where a is the real part and bi is the imaginary part. So let's take a look at adding and subtracting complex numbers. Right here we have the quantity 5 minus 7i plus the quantity 2 plus 4i. So because this is a plus in between both of these binomial terms, we can actually remove our parentheses. So we have 5 minus 7i plus 2 plus 4i. At this point, it's just combining like terms. The i's will go with the i's. The non-i's go with the non-i's. So 5 plus 2 is 7. Negative 7i plus 4i is negative 3i. The real part comes before the imaginary part. So the final answer for this one is 7 minus 3i. All right, taking a look at this example, we have quantity 4 minus 8i minus the quantity 3 minus 6i. Because we have this subtraction here, we need to distribute it to everything inside that second term, that second binomial term. So 4 minus 8i minus 3 plus 6i. Once we've distributed that negative, we can now combine our like terms just like the previous example. So now we have 4 minus 3, which is 1. Negative 8 plus 6i is 2i. So this answer becomes 1 plus 2i. All right, so let's go on. Now we have what we call complex conjugates, and this is very important because this is where we start multiplying and dividing those complex numbers. So complex conjugates are two complex numbers of the form a plus bi and a minus bi when they are multiplied. The complex conjugate always gives a real number. So what does that mean? Well, let's take a look at this example here. When we're dividing these complex numbers, we have 2i over the quantity 3 plus I. This denominator is that a plus bi. So I need to multiply by the complex conjugate to get the I out of the denominator. And that's the thing. I do not want any I's in the denominator. So the complex conjugate of 3 plus 6I is 3 minus 6I. Well, if I am multiplying my denominator by 3 minus 6I, I need to multiply my numerator by 3 minus 6I, just to keep it equivalent. And in reality, all I'm really doing is multiplying by 1. Because when I have the same number on top as bottom, it simplifies to 1. All right, so let's take a look. So now we have 2I times 3, which gives us 6I. And we have 2I times negative 6I, which gets us that negative 12I squared. So there's our numerator. Now for our denominator, we have two binomial terms, which means we need to distribute 3 times 3. That gets us 9. 3 times negative 6I, which gives us negative 18I. 6I times 3, which gets us positive 18I. And 6I times negative 6I, which gets us that negative 36I squared. All right, let's see if we can simplify anything out. Well, I know that I squared is just negative 1. So anywhere I have an I squared, I'm just going to put negative 1. All right, so now let's see if we can simplify anything further. We have 6I minus 12 times negative 1. Nope, can't simplify anything there. So 6I minus 12 times negative 1. But when I take a look at the denominator, I have 9 minus 18I plus 18I. So what happens is these middle terms are going to cancel out. And here's a trick. It's always going to cancel out. And that's what the beauty of a complex conjugate is. So now I'm just left with 9 minus 36 times negative 1. Well, when we simplify this down further, we have 6I plus 12, because negative 12 times negative 1 is positive 12. And then 9 plus 36. All right, I'm going to come over here so I have just a little bit more room. So now I have 12 plus 6I over 45. Well, we need to simplify this down a little bit further. We have a binomial term of 12 plus 6I over a monomial term of 45. So to simplify, we're going to actually separate this fraction out. 12 over 45 plus 6I over 45. And when we take out our handy dandy calculators, 12 divided by 45 simplifies down to 4 over 15. And then 6 over 45 simplifies down to 2 over 15. And this is where we tack on that I value. And there we have it, friends. That is our final answer for simplifying that complex number. All right, well, let's go over here. This time we have a 5I. Well, because it's not a complex number in its own right, because it does not have the A plus BI, we can multiply it by itself. When we multiply a monomial imaginary number by that same monomial magic number, it will yield a real number. So we have 5I times 4 and 5I times I squared. So we get 20I plus 5I squared over 5I times 5I, which is 25I squared. Well, just like before, anytime I see that I squared, I'm going to put a negative 1. That's going to help me out. So now I have 20I plus 5 times negative 1 over 25 times negative 1. So when we simplify this out, we have 20I minus 5 over negative 25. And just like that previous example, we are going to divide. Separate these out and divide. All right, so we have 20 I over negative 25. And then we have negative 5 over negative 25. And so when we simplify that out, we have negative 4/5 I plus 1/5. However, what's the problem with this complex number? Would I mark this wrong or would I mark this right? If you said wrong, I hope you can tell me why. Complex numbers have to be in the form of A plus BI. Right now we have BI plus A, so you would get this marked wrong. That A value always has to come first. So we have 1/5 minus 4 over 5I. And that, my friends, is your final answer and our last example. If you have any questions, please reach out. Have a great day.